Good afternoon, greeters. My name is Temba Nube, and welcome to our live broadcast session for Physical Sciences, which is proudly brought to you by Free State Department of Education in collaboration with Pagama Research and Development. So we are fast moving towards the final exam, the National Senior Certificate. With that said, our live program seeks to actually prepare you, towards, enhancing your level of readiness in as far as the final exam is concerned. So this session is essentially for you, designed for you, and everything that we are doing in the session is designed in such a way that it supports you so that you develop the level of confidence that is much needed leading to the exam that matters the most on the 8th of November, which will be your paper 1, and then on the 11th, which will be your second paper. So kindly take note, just to get this out of the way, on the 7th, which is the eve of the physics paper 1, we'll have a live broadcast, which is the just in time, just to prepare you, go over some techniques, the tips, so that you are more than prepared come the Friday of the 8th. And then once you are done writing the paper 1 on the 8th, the very same afternoon, because on Monday we are writing paper 1 on the 11th of November. So it means on the 8th at 3:30 we're crossing live again to yet another live broadcast session for the chemistry focus. Right, so what is it that we want to actually do today? We want to focus our attention on the physics, but which aspects of physics are we looking into? We're looking at electricity and magnetism, which is subdivided into 3 big topics in paper 1, physics, which is your electric circuits, your electrostatics, as well as your electrodynamics, which is the electrical machines, motors and generators, as well as alternating current. So for the purpose of today, we'll just confine our attention to the circuits as well as the electrostatics. Electrostatics is your Coulomb's law, your electric fields, and electric field at a point. Right. Okay, so there is nothing new in as far as the slide is concerned. So today our focus is on this portion of the 55 marks, which is the largest after mechanics. Mechanics is the 65 marks out of the 150, and then the 55 is based on your electric circuits, electrostatics, and electrodynamics, as well as alternating current. So but today we're only looking at circuits as well as electrostatics. Right, okay, now just a reminder once again, so that this becomes commonplace in our preparation, so that we assume a uniform approach in as far as our live sessions are concerned. We'll always take time to remind ourselves of what is important. The examination guideline that we shall draw attention to is the one dated 2021, right? So take note of that. So the exam guide that you should use as a checklist is the 2021 version, right? Now remember, in terms of the quick wins, why is it important that I refer you to your exam guide? Is because of the low-hanging fruits or the quick wins. These are your easy type of marks that everyone must be in a position to collect and accumulate. Now, so every long question in section B, which is the structured question, will remember some recall, would demand or require you to remember a definition or two. These are your easy marks, which is your 2 out of 2 or 0 out of 2. Okay, so let's talk about the technique once again. Yes, our focus is on electric circuits as well as electrostatics. What you need to remember is the fact that in the 10 minutes reading time between 8:50 and 0900 hours, you are scanning through that's the reading time. You are scanning through the question paper. In the process, you are identifying questions that are potentially easy, or where you feel on the day you are able to collect the most marks. Okay, then these are the questions that you start with. Okay, do not leave the multiple choice blank, but for us to be able to successfully attempt the multiple choice, it's also important for us to get the technique right. So a part of our today's session will obviously focus our attention on that aspect, right? So when you define, take note of the keywords, okay? And ensure that the keywords are used in the correct context, okay? Very, very important. We'll make practical examples in as far as this is concerned, right? So today we'll start with the electric circuits. So from grade 11, remember grade 11, we dealt with the Ohm's law, okay, which says V is equals to I times R, right? This is the mathematical representation of the Ohm's law, okay? There'll be variations of the same law in terms of R is equals to V over I, or I is equals to V over R, okay? So essentially, the Ohm's law talks about the potential difference or the voltage across the ends of a conductor is directly proportional, these are the keywords, to the current at constant temperature, right? So in long questions, which would be typically your question 8 in circuit, you might be called upon to state the Ohm's law, okay? Include the keywords. The keywords must be used in the correct context, okay? And then you are also required to determine the relationship between current, potential difference, and resistance at constant temperature using a simple electric circuits, right? We must be able to distinguish between ohmic and non-ohmic conductors. So ohmic conductors are the type of conductors that obey Ohm's law. Then obviously a non-ohmic conductor is the one that does not obey Ohm's law, right? We'll look into the differences and similarities, if there are any, between the two. And then you are supposed to solve problems, okay, using series and parallel circuits, a maximum of 4 resistors, right? Okay. Then electrical power, it's another part that we also looked at in grade 11, right? So power in terms of rate at which work is done or energy is expended. So rate at which work is done. So if you say W over delta T, this is rate of work done, which is the same as rate at which energy is expended. So to expend energy, let's take for example in the context of your electric circuits, you have a light bulb connected at a point. So once the circuit is complete, the source of electrical energy is the battery, okay? And then the battery transforms the chemical potential energy inside it to electrical energy, which results in the flow of charge. So once that electrical energy through the conductors reaches the light bulb as a resistor, it transforms or converts electrical energy into light. When energy is converted from one form to another, work is done. So work is energy, okay? And energy is work. In other words, we can think of energy as the capacity to do work. So when there is transformation of energy or conversion of energy from one form to another, work is done. So in the context of electric circuits, if you've got a heating element is a resistor. What it does, it converts electrical energy into heat. Take for argument's sake a speaker. You know, you talk about purely resistive circuits in the context of electrodynamics, or those AC, circuits, which is very much applicable in our homes. If you have a speaker in an electric circuit connected in series, a speaker is a resistor. It converts electrical energy into sound. So if we say, for argument's sake, a speaker is 150 watts, what does that mean? It means it converts 150 joules of electrical energy into sound per unit time or per second. Now let's take a very powerful speaker, which is what? 100 times bigger than that, which is 1,500 watts. So it will convert 1,500 joules of electrical energy into sound, in 1 second. Per unit time, in a unit of time, we've got 1 second. That's how long a unit of time is. So that's why a speaker that's 1,500 watts is more powerful compared to a 150 watts. And I'm saying powerful, I'm referring to the power. So the power in the context of circuits is not how strong as we talk about it in acids and bases. So here we're talking about how much work is done or how much energy is expended in a given period of time. All right. So then there will be variations of the power formula in the context of circuits, right? We'll also solve electrical problems and deduce that the kilowatt hour, this unit is very, very important, refers to the use of 1 kilowatt of electricity. A kilowatt is 1,000 watts. So 1 kilowatt is equals to 1,000 watts. Okay, so if we say we've got 2.5 kilowatts, that's like 2,500 watts, right? And then also the cost of electricity, right? Okay, and then we'll look at, in grade 12 we looked at these problems which involve series parallel networks. Okay, but more importantly, we defined EMF as the maximum. The word maximum is key. Maximum energy provided by the battery per unit charge passing through it. So remember, EMF is voltage, and voltage is W over Q. All right. So if a battery has an EMF of 1 volt, what does it mean? It means it can provide or supply a maximum energy of 1 joule for every coulomb of charge. Equivalently, in a car, we've got a 12-volt battery, right? So what this 12-volt battery does in an automobile or in a car, it means it does the EMF. So it supplies a maximum of 12 joules of energy for every coulomb of charge or per unit charge. So if 1 volt is equals to 1 joule per coulomb, then 12 volts is equals to 12 joules per coulomb of charge. Right. So the key word is maximum energy or work. Why work? Because energy is work. Remember, energy is measured in joules. Also, work is measured in joules. Okay. So if you contextualize work in terms of your circuits, we're talking about energy expended, right? Or energy conversion from one form to another, thereby work is done, right? Okay, now we briefly spoke about ohmic conductors. These obey Ohm's law. Okay, so and now if we're saying that a conductor is an ohmic conductor and it obeys Ohm's law, it therefore demands us to remember what the Ohm's law says. We have to know what the Ohm's law says to classify a given conductor as ohmic or non-ohmic. So an ohmic conductor, the resistance of the conductor remains constant. Why does it remain constant? Because R is equals to V over I. So the voltage across the ends of the conductor is directly proportional to the current. Then a non-ohmic conductor does not obey Ohm's law. That's the key thing. So these are the key differences. Now, a light bulb is a non-ohmic conductor, right? The resistance of the light bulb does not stay the same. As the light bulb is glowing or doing work, what does happen is that its temperature increases. So remember, Ohm's law states that at constant temperature, the relationship is only true. The relationship of V is directly proportional to I when temperature is constant, right? So this is what the law says in as far as the ohmic conductors, right? So we've spoken about the power there, a rate at which work is done, right? So the watt is in uppercase there, which is a capital letter because it's somebody's name. So it will be 1 watt, okay, which is the watt is W-A-T-T, which is equals to 1 joule per coulomb, right? And then the kilowatt hour in terms of terminology, very, very important. If we are talking about the kilowatt hour as a unit, this is the use of 1 kilowatt of electricity for 1 hour. So it has a duration. It's not kilowatt per hour, it's kilowatt hour. Okay, how it means the usage of 1,000 watts of electricity in a duration or in a period of an hour. That's why it's kilowatt hour, not kilowatt per hour. That's often a mistake. Okay, then we've spoken about EMF, and then the internal resistance of the battery, which one that causes a drop in the potential difference of the battery when there is current in the circuit. So in other words, if we have got a battery like that, okay, and then this battery is connected to a simple circuit like this. Okay, let's say it's a light bulb there. Okay, and then we connect a voltmeter across the ends of the battery like that. Okay, the voltmeter reading across the terminals of the battery when there is zero current, in this case, becomes the EMF. But then if we decide to close the switch, and then this battery has got internal resistance inside, it means there will be a drop in the terminal potential difference compared to the EMF value. Okay, so in other words, we are saying V external, which is the terminal potential difference when there is current in the circuit, should be less than EMF, okay, which is E, because E is divided between V external and V internal. In other words, what we are simply saying is that the internal resistance of the battery is in series with the external resistance. So the maximum voltage is divided between internal voltage as well as external voltage because they are in series, right? Now, terminal potential difference is what we would refer to as V external, right? Okay. All right, now let's take some time to talk about, resistors that are in series. Very, very important. What is typical about this is that suppose this is our positive terminal and this is our negative terminal of the battery. Conventional current flows in that direction, right? That's our current, right? Same current. So you can see here the color coding is the same throughout. Okay, it means the amount of current in the circuit remains the same. So in other words, we are saying current through R1 is equals to current through R2, which is equals to current through R3, which is the one that suggests current is the same. All right, and then voltage is divided. Suppose we've got this, that's V1, okay, that's V2, that's V3. Now we are saying that if this is V terminal potential difference total, right? So we're saying that V total is equals to V1 plus V2 plus V3. So it means the terminal potential difference is divided between the three external resistors, right? Suppose this battery had some internal resistance. It means therefore this is V external, okay? Therefore it means that E is equals to V external plus V internal. So the EMF is the one that is split between those four resistors. Why four? Resistance of the battery, one, and the three external resistors. Okay? And then multiple choice is another area that is very important, and earlier on we would have alluded to it to say there's need for us to actually practice it and understand it. So I'm going to give you 2 minutes just to try and respond to this question. Just 2 minutes. Eliminate the distractors, study the circuit, and understand it. I'm going to give you 2 minutes just to try that. Your 2 minutes starts from now. Welcome back, grade 12s. I hope you have done your attempt insofar as this question is concerned. Now let's take time just to go through the question with a particular focus on the technique in which you respond to multiple choice questions, particularly those that involve circuit diagrams, right? So it says here the diagram below represents a circuit in which all external resistors have the same resistance, right? So there are 4 resistors external, which is, let's call this one 1, let's call it 2, let's call it 3, let's call it 4. So it means R1 is equals to R2 is equals to what? R3, okay, is equals to what? R4. Hence we'll call them, each one of them R. All right. Now it says which one of the ammeters in the circuit have the lowest reading. So which means we're looking for the one that will have the least current or the smallest current, right? So by convention, current flows from the positive terminal. I'm going to trace that through that ammeter, right? So when the current reaches that part, I'm going to change the color just to highlight the difference there. Okay, then here is a different color. Okay, that's a different color there. Okay, there's a different color, and then when it gets there, we go back to our colors, and then we go back to red. There it is. Okay, right. Now let's understand here what is happening. So red is the total current, which is the maximum. So A1, reading of A1 is equals to the reading of A2, which is the current total, right? That's the total current. And then let's agree, R1 and R2, they give us 2R because they're in series. So I'm looking at the parallel. I've got R3, okay, which is in parallel to R1 plus R2. In other words, we've got R3 as R, and then R1 and R2 as 2R, right? So the current that goes through R1 and R2 is half the current that goes through R3. In other words, the current for R3 is twice the current for R1, which is equals to twice the current for R2, because the current for R1 is equals to current for what? R2, because they're in series, right? So it means A3 will have the lowest reading of current. Why? Because it has got twice the resistance. Okay, there is twice resistance in that path, right? So I'm not going to look at A1 and A4 because current for A1 and current for A4 is the same. So the correct option therefore is option C. That's what we need to understand, that A3 will register the lowest current. Why? Because in that pathway there is greater resistance, or the current passing through R1 and R2 is half the current passing through R3. It is for that reason that A2 reading will be twice the reading for A3. So A2 is equals to 2 times A3, while A1 is equals to A4, right? So I think that kind of makes sense, right? And then having said that, let's move to resistors in parallel. Okay, so these are parallel resistors, right? These are parallel. Okay, let's get that right. Okay, so in this case, suppose this is V total across the source. Okay, let's say this is V3, say this is what, V2, and then let's say that is what, V1. Okay, so V1 is equals to V2 is equals to V3 is equals to V total. Okay, this is what we mean that when we say that in a parallel combination of resistors, voltage will remain the same, right? That's what is important. Okay, and then what do we mean when we say current is divided? Okay, suppose this is our positive terminal and this is our negative, so current will flow in that direction. Then there is a split here. Okay, then there is another split there. Okay, and then there is that current. So it means this is a current divider. So we say that this is a current divider. Okay, so a series circuit, sorry, a parallel circuit is a current divider. Now, the amount of current passing through each one of those pathways or each one of those resistors depends on the resistance. If these resistors were identical, okay, it means they will all share the current equally. Okay, but if one has got greater resistance and the other one is less resistance, the one that has got greater resistance will receive the least current. So the higher the resistance, the lower the current for the same voltage, which is only possible in a parallel combination of resistors. Right, and then the formula sheet is another very important aspect of our, our paper one in terms of the circuit. So if you look at this formula sheet, just to familiarize ourselves with, this is the Ohm's law, right? Now this is for series resistors in series, and then this is for resistors in parallel. Okay, while talking about the parallel, remember, for any two resistors in parallel, okay, we are happy to say R parallel or their equivalent or effective resistance is equals to R1 times R2 over R1 plus R2. Okay, this is only for two resistors in parallel, because you end up forgetting to swap, especially when you use this formula, okay, to actually remove the reciprocal, right? So we are happy with that. Okay, and then the EMF is equals to IR, still comes from the Ohm's law, because EMF is V, current is current, and then the sum of those two is R. Okay, so it's still the Ohm's law. The equation E is equals to I R plus R. But don't forget again, it's E is equals to V external plus V what? Internal. Where is this coming from? E is equals to I big R plus I small r. Okay, and then this is the definition of current in terms of current is equals to rate of change, the rate of charge flow. Okay, the rate at which charge flows. And then these are the different variations of the power formula. From the power formula, we are able to calculate energy expended, voltage, current, and amount of charge given the time. All right. So that's very, very important. Now, in terms of problem solving, the algebraic sum of the changes in potential in a complete transversal of any loop in a circuit must be 0, right? So this is the algebraic sum. We'll try and actually look at this equation in the context of its application. All right. Now, so always write down the formula of equation that solves the question under consideration, and then here we shall draw attention to the data sheet. Okay, find the unknowns if needed. This is multi-concept problem. These are 4 marks and above and more. Okay, and then do calculations and write down the final answer, including the correct SI unit. Okay, very important. Okay, now let's look at this practical worked example to see how best we can apply the strategies that we spoke of in the previous slide. We've got 3 resistors, 2 ohms, 4 ohms, and RS connected to a battery as shown in the circuit diagram below. With switch S1 open and S2 closed, the reading on the voltmeter is 10 volts. Both switches closed, the reading is 8 volts and the ammeter is 1 ampere. Right, if we close, so it means with the switch open, okay, 10 volts. So this 10 volts is actually what? The EMF. Okay, it's a given. Then if we close both switches, okay, switch S1 and S2, the reading on V changes to 8 volts. So it means V external is equals to 8 volts. Now, based on this data that we've collected, I think we are able to determine what we call the V internal. Okay, so from the equation, E is equals to, we are analyzing the circuit, we're not answering any questions yet. So E is equals to V external plus V internal. Okay, so E is equals to, okay, it's 10 is equals to 8 plus V internal. So our internal or lost volts, as we would call it, is equals to 2 volts. Now the ammeter reading is 1 ampere, right? It's 1 ampere, all right? So this is the total current. So I total is given as 1 ampere. Okay, now the 8 volts is divided between this V parallel, right, and this Rx, this unknown voltage. Let's call it Vx. All right, let's call it Vx. So how much current passes through Rx? It will be 1 ampere, right? Now also we can immediately tell that the 1 ampere is split between the 4 ohm resistor and the 2 ohm resistor. But what is it that we know? We know that the 4 ohm resistor will have half the current as that passes, which passes through the 2 ohms. Okay, or the 2 ohms will have double the current that passes through the 4 ohms. So in a nutshell, we now have a clear understanding of what exactly we are dealing with in terms of this circuit, as we are saying. Now write down the values of the EMF of the battery, and then this is 1 mark. I want you to pay attention to the mark allocation. So from the data that is given, the voltage across the battery when there is no current is the EMF reading. Very important, is the EMF reading. Okay, so in this case we were told that when both switches were open, the voltmeter reading was 10 volts. So therefore E is equals to 10 volts, as we would have seen it here. So here is what we collected in terms of our data. Okay, it has in many ways made our work much easier, right? Okay, and then if we move forward, calculate the resistance of the unknown resistor Rx. Okay, this is what I'm going to do. This is by far the longest question. Okay, so I'll give you 5 minutes to try that question. I'm going to write it down to say find the resistance of Rx on this side, so that you can see the question. Okay, this is question number 1.2.1. okay, 1.2.1, and calculate the resistance Rx 7. Okay, so the 7 minutes, the 5 minutes starts now. I'll give you 5 minutes. Just try based on the discussion that we have had to try and get the value of Rx in the circuit, as we have carefully dissected the circuit so that we make it easier for you. I'll give you 5 minutes starting from now. Welcome back, grade 12. Let us look at the long question where you are supposed to determine the resistance of Rx, which is unknown. All right. So already we can find the effective resistance of the parallel combination of resistors, the 4 ohm and the 2 ohm. I'll tell you why we are doing that. Okay. So if we go to our feedback, so we will say R parallel is equals to R1 times R2 divided by R1 plus R2. Okay, so this is 4 times 2 over 4 plus 2, right? So R parallel in this case becomes 8 over 6. Okay, that's 8 over 6, which is 4 over 3, right? 8 over 6 is 4 over 3 ohms, right? So whatever that works out to, but I'll prefer to leave it like that for now. Then we can calculate V parallel after that. So V parallel is equals to total current multiplied by R parallel. Okay, so the total current is 1 ampere. R parallel is 4 over 3. So it means V parallel is 4 over 3 volts. Okay, which is 1,33333. All right, fine. And then if we go back to that circuit, what do we realize? We realize that the V external is 8 ohms. So the 8 ohms is split between R parallel, okay, and Rx, right? So in other words, what we are saying is for this circuit, we've got this R parallel, okay, R parallel, as well as Rx that we don't know. Okay, right? So we understand that the sum of these two is 8 volts. So this is V parallel, and then that is what? Vx, right? So Vx in essence is equals to 8 minus 4 over 3, which is equals to, so if you go to your calculator, we'll have 8, okay, minus, okay, 4 over 3. Okay, this gives us 20 over 3. 20 over 3 volts. So that is Vx. And we know the current that passes through Rx, which is 1 ampere. So in other words, Rx is equals to what? Vx over current. Okay, so Vx is 20 over 3, okay, divided by 1, which is equals to what? 20 over 3. So 20 over 3, it works out to 6,67 ohms, right? So that's the magnitude of Rx, right? If we go back to the circuit, we also want to determine the internal resistance of the battery, right? So for us to determine the internal resistance of the battery, let's also pay attention to the mark allocation, which is 3 marks, right? So if it's 3 marks, we are saying E is equals to I, okay, R plus R, okay. E is 10, right, is equals to what? I, which is 1. So R is equals to 20. We have to use Rx, which is 4 over 3. So total resistance in this case will be R series parallel plus R series. Okay, R parallel plus R series. So R total, which is the total resistance in this case, becomes our R parallel is 4 over 3. All right, 4 over 3 plus Rx, which is 20 over 3. 20 over 3. So R total is equals to 20 over 3 plus, okay, 4 over 3. Okay, this gives us 5. So our total is 5 ohms. So we'll use 5 there plus R. Okay, So 10 divided by 1 is 10. 10 minus 5 is equals to R. So our internal resistance is equals to 5 ohms. Right. Or we can choose to use this alternative because we know the lost volts, because we've got V internal, which is equals to 2 volts. Okay. So it means therefore V internal is equals to I multiplied by R. Okay. The lost volts is 2. Okay. All right. The lost volts is 2. Then the current is 1 multiplied by R. Okay, here we're getting 2 ohms. Okay, let's go back to that and rectify that. Okay, E is 10. Okay, that is 5. The total resistance is 1, and then the total current is 1. We're told that the current passing through that is 1. Let's go back to that. Okay, the ammeter reading is 1 ampere. All right. Okay, so if that's 1 ampere, and then the lost volts is equals to 2 volts. Yes, 10 minus 8, which gives us 2. We are verifying because we need to get exactly the same answer. All right, and then EMF is 10 volts. The total resistance, is 5, or 5 plus. Okay, this is 5 plus. Okay, this is 5, which is R total, which means therefore if we say 4 over 3, which is R parallel, plus just to confirm that 4 over 3, okay, plus, okay, 20 over 3. Okay, what do we get there? We get 1 over 5. Oh, okay, that's 1 over 5 instead. Yes. Okay. Oh no, say divided there, so we should actually delete that and say plus. Okay. All right. Okay, just one moment. Plus. Okay, this gives us 8 instead. This is 8. Okay, so it's 5 minus 8, which gives us the 2 ohms, exactly as the other one, which says, we said V internal is equals to I times R. Okay, so V internal is what? V internal is 2 volts, the current is 1 multiplied by R, so internal resistance is equals to 2 ohms, which is exactly that. Okay, very important just to verify that. And then the question goes on and says, how will the reading on the voltmeter be affected if switch S1 is closed while switch S2 is open? Okay, let's go back. We close switch S1 and open switch S2. It means therefore, number 1, total resistance will increase. Okay, if we increase the total resistance in the circuit, what must happen to the total current? It means current will decrease. Okay, so if the current decreases, it means the ammeter reading will also be lesser, right? Okay, so that's as far as that question is concerned. Now let's look at this individual activity, which also talks about circuits, but also incorporates some aspects of electric power, which is very, very important from grade 11. So we've got 3 electrical devices, X, Y, and Z, which are connected to a 24-volt battery with internal resistance R. So E is equals to 24 volts, right? So what does it mean? It means this 24 volts suggests to us that the battery can supply a maximum of 24 joules per coulomb of charge. Okay, take that into account. The power rating of each device, if devices X and Y is indicated, right? With switch S1 closed and switch S2 open, the devices function as rated. Calculate the current in X. Okay, we want the current in X, right? That's 3 marks, so it's gonna be formula. Okay, that's 1 mark. Substitution, it's another mark. answer, another mark. That's 3 marks. Okay, and then they want us to calculate the resistance of Y. Okay, it's another 3 marks. So I'll give you the next 5 minutes to try the 3 questions that are given there, and then we'll take a quick discussion before we go for a quick break. We'll start our 5 minutes now. Please do attend the questions, and then when I ask you to stop, and please do so that we take a discussion and correct where we might have potentially go wrong, so that we don't make the same mistakes. Your 5 minutes starts from now. Welcome back, learners. Let's take a quick discussion on this question, and then we can take a short break after that. Coming back, then we'll look at one typical problem on electrostatics. Right, so switch S1, so switch S1 and S closed and S2 open. S1 is closed. Okay, let's close switch S1, and then S2 is open. It means the only resistors that we have in this circuit is resistor X and resistor Y. Now, how are these resistors connected to each other, right? We need to also ask ourselves that question. If you look at resistor X and resistor Y, they're connected in parallel. So V across X is equals to V across Y. We cannot talk of Z in this case because Z is out because of switch S2 is open. So this must be equal to V external, right? Calculate the current in X, right? So if we want the current in X, we've got 20 volts and then the power rating there of 100 watts, okay? So we know that P is equals to VI, right? 100 is equals to 20 multiplied by the unknown current. So the current through is equals to 5 amperes, right? So that's formula, that's substitution, that's answer, including the correct SI unit, right? Okay, that's straightforward. And then the resistance of Y, okay? Based on the fact that we know the voltage across Y, right? We know that V across X is equals to V across Y. Now, this is equals to what? 20 volts, right? So this question requires us to calculate the resistance of Y, right? We're given the power and we know the voltage. So P is equals to V squared over R, right? So that's 150 watts is equals to 20 squared over R. So R is equals to 400 over 150, which gives us what? If we go to our calculator, okay, it's 20 squared, okay, divided by 150, okay, this gives us 2.67 ohms, okay. That's the value there. Okay, 20 squared equals to 400 divided by 150, just to confirm. Yes, it gives us 8 over 3 ohms. That's the resistance. So it's formula, substitution, and answer. That's another 3 marks there. Okay. Then internal resistance of the battery, right? We need to calculate the current passing through that so that we can get the total current, because we got the current in X to be 5 amperes. Okay, current in X is 5 amperes, right? Now current in X is 5 amperes. Then current in Y is equals to V over R, okay, Y. So current through Y is equals to V is 20 over 8 over 3, okay, to be exact. So we will say 20 divided by 8 over 3, which gives us the 2.67, 8 over 3, okay. This gives us 15 over 2, which is equals to 7.5 amperes. So the total current in the circuit is equals to 5 plus 7.5 amperes, okay, which is equals to this plus 5. Okay, this gives us 25 over 5, which is 12.5 amperes. 12.5 amperes. Therefore, E is equals to I R plus R. Okay, then it therefore means it's 24 is equals to 12.5. Okay, our total resistance in that case is we have to find the total resistance as well, which is parallel. R parallel is equals to Rx times Ry over Rx plus Ry, which is equals to the resistance of the first one is which is Rx. Rx is given to be, if we can go back, the resistance of X, or we didn't calculate the resistance of X, but I think there are ways that we can get the resistance of X even though we don't have it. The one that we have is resistance of Y, right? So if we have the resistance of Y and the resistance of X, then we've got the total external resistance, right? Okay, then this is 2,67, okay, multiplied. Resistance of X is something that we can get Rx, okay, because we know that P is equals to I squared R. So that one is 100 power, okay. The current for X is 5 squared multiplied by R. So R is equals to actually 100 divided by 25, which is 4 ohms, okay. This plus 4, okay, multiplied by 4 over 2,67 and plus 4, right? Okay, so it's 2,67, okay, times 4, okay, is equal to that, divided by 4 plus 2,67, which is 6,67, okay. This gives us a total resistance of 1,6. So R parallel is equals to 1,6 ohms. So this is 1,6, okay, plus R. So it's 24 divided by 12.5, okay, then minus 1,6, okay, that gives us the internal resistance of 0,32 ohms, right? So that's how we actually do that. So this is, if you go back to the question itself, you do realize that this is 5 marks. It therefore means it is indeed a multi-step type of a problem, right? With that said, let's take a 3 minutes breather. Then when we come back, we shall look at one of the questions in as far as electrostatics is concerned. See you after the break. Welcome back from our short break. Let's look at, without any waste of time, let's look at electrostatics, which is your typical question 7, as well as the multiple choice section. So we'll use this as an example, which is your worked example, just to guide and also remind ourselves of what is important. So the diagram below shows charge P2, which has got a charge of 2 microcoulombs, right? So remember, 1 microcoulomb is equals to 1 times 10 exponent minus 6 coulombs. Okay, 1 nanocoulomb is equals to 1 times 10 negative 12 coulombs. 1 picocoulomb is equals to 1 times 10, and this is minus 9, nano is minus 9, then this is minus 12 pico, which is the coulomb, right? Calculate the force between P and Q. So P exerts a force on Q, an electrostatic force, right? So Q is negative, P is positive. So they exert a repulsive, an attractive force towards each other. Okay, so if we were to draw the force diagram, so this is the force by Q, force by Q on P, and then this one is the force by P on Q, right? So according to Coulomb's law, F electrostatics is equals to K Q times QP over R squared. That's the formula. So the electrostatic force, therefore, 9 times 10 exponent 9 multiplied by 2 times 10 exponent negative 6, then 4 times 10 exponent negative 6. Okay, take note, we did not put the minus because we know that the minus for the charge will mean the direction. So the force diagram or the free body diagrams that we've drawn serve to suggest the direction so that we don't mess it up, right? So if we go back there, the distance between them is 13 millimeters, right? So if it's 30 millimeters, it's going to be 30 times 10 exponent minus 3, and then we squared. So the electrostatic force, therefore, if we go to the calculator, it will be 9 exponent 9, okay, nine exponent 9 multiplied by 2 exponent negative 6 times 4 exponent negative 6 divided by 30 exponent minus 3. Okay, we have to square that, right, because it's the square of the distance. Okay, close bracket, and then we square it. So this gives us 80 newtons. So the electrostatic force, its magnitude is 80 newtons, right? So this force is 80 newtons, force by Q on P is 80, force by P on Q is 80, force by Q on P is 80, because they are equal in magnitude and opposite in direction. Okay, without calculating the force between R and Q, right? Determine how many times, by how many times will which factor will smaller or greater. First of all, remember, if the distance is 30 millimeters and then the distance has been squared, if we double the distance, so now the distance is 2r, okay, it's twice as much, so the force will be a quarter. If we double the distance, the force will be a quarter, right? And then what has happened to the product? The product was 2 times 4, now is 4 times 6. So initially the product of the forces was 8, okay, now the product is what? 24. Okay, so we have increased it 3 times. Okay, so remember, it's directly proportional, so it means this force, the new force, will actually be 3 times a quarter F, right? So it means if the product is 3 times and the force is a quarter, it's actually, if the force is doubled, it means the force will be a quarter. Now, if you multiply the two, the new force will be multiplied by a factor of 3/4F. So it will decrease and become 3/4 of the original force. This is based on the fact that we appreciate that the electrostatic force is directly proportional to the product of the charges, okay, and inversely proportional to the square of the distance. Right, it's a very good question. Okay, and then draw a free body diagram to show all the forces on Q. Okay, forces on Q. Okay, there are how many forces that exist? So if there was a mark allocation, we were going to be able to actually draw, to know how many forces must be included, right? So in other words, we are saying if this is Q, there is a force that P exerts on Q. The force by P on Q, because this is positive and this is negative, while Q is negative, right? So there is a force that is exerted by P on Q, force by P on Q, okay? Then while Q is negative, the other charge, which is charge R, repels Q to the left as well. So this is another force, okay? This is the force exerted by what? R on Q. And then we also have this force, which is the gravitational force. So there will be 3 forces there. Force by P on Q, force by R on Q, and then the weight. This will give you the 3 marks, right? Okay, and then what is the resultant force on Q due to the presence of P and R, right? So the resultant force, it means now we have to find the force in terms of all the forces that are acting on Q. We have calculated the force by P on Q. It's 80 newtons, right? And then the other one, it's in the same direction. So F net or F resultant is equals to what? F by what? By P on Q plus F by R on Q, right? So it means F net is equals to 80, okay, plus 3/4 80, because F is 80. So 80 plus 3/4 times 80. Okay, this gives us 140. So it's 140 newtons to the left. Why to the left? I'm going to disregard the gravitational force. Both forces act to the left, right? And then moving along, okay, now R is removed and P and Q are moved up against each other, then move back to their original position. Calculate the charge that P and Q now have, right? This is very important when it comes to the principle of conservation of charge, which states that in a closed system, in an isolated system rather, the net charge remains constant during a physical process. So the Q nu in this case will be equals to Q net divided by 2. Our net charge in this case is going to be 2 plus minus 4, right, over 2. Okay, this is equals to minus 2 over 2, which is negative 1 microcoulomb, or 1 times 10 exponent minus 6 coulomb each. That's negative, right? So if you check, before contact, the net charge was negative 2. After contact, minus 1 microcoulomb plus minus 1 microcoulomb will also give us negative 2 microcoulomb. So it means before the physical process, which is the contact of the two charges, and after, the net charge was indeed kept the same. That's what the principle of conservation of charge suggests. Now, if you look at the follow-up question, it says, calculate the number of electrons transferred. This is a very important question because it speaks to what we refer to as the principle of quantization of charge. What does the principle say as we know it from grade 11? It states that every charge in the universe is an integer multiple of the elementary charge. It means Q is equals to N multiplied by E, where E is the elementary charge of negative 1,6 times 10 exponent negative 19 coulombs. Right. So let's agree. Charges, electrons are transferred from Q to P. Why? Because Q is more negative. Right. So if we are to calculate the number of electrons transferred, okay, so number of electrons is equals to delta Q over E, right? Delta Q is the final charge, negative 1 times 10 negative 6, okay, is equals minus, we can take either a P or Q. Let's take P for argument's sake. P was 2 times 10 exponent minus 6 divided by, so P gained electrons from Q. It means then therefore we'll divide with the negative 1,6 times 10 minus 19 coulombs. Right? So negative 1 times 10 exponent minus 6 minus 2 is minus 3 times 10 exponent negative 6 divided by negative 1,6 times 10 exponent negative 19. It means we must get a positive integer. So it's negative 3, okay, negative 3 times 10 exponent negative 6 divided by negative 1,6, okay, times 10 exponent negative 19, which is the elementary charge. This gives us a number of 1,875 times 10 exponent 13. This is a positive number, electrons transferred. Okay, so what do we mean here? We mean that this number that we've calculated is equal to the number of electrons that were transferred from P to Q, which is exactly the same number that Q lost to P, which is the same number that P gained. So the number of electrons lost by Q equals the number of electrons gained by P, which is equals to the number of electrons that are transferred between the two charges, according to the principle of conservation of charge. And while we appreciate that charge is quantized, so it means every charge that we can quantify is in integer multiples, or it's in whole number multiples of the elementary charge. So this is more like your grade 10 and 11 stuff that you need to also remember. Now, because of time constraints, there is a worksheet activity that was shared with your teachers. It has got more worked examples and individual activities that you can attempt at leisure as part of your practice. So wherever you hit the wall, I think your teachers will also be readily available to support you. Now, because of time constraints, this brings us to the end of our session. See you next time, next week. It's goodbye for now.